Alright, in this video, we are going to tackle on one example, 2x2 exchange economy, just for, summarizing our discussion in the previous long video and enhancing our understanding about the excess demand function. Alright, so now consider 2x2 exchange economy where there are two consumers A and B and just two goods. Okay? So it's a 2x2. And consumer A's utility function is given by Cobb-Douglas, x1a times x2a, and consumer A's initial endowments are 4,2, 4 units of good 1, 2 units of good 2. And consumer B's are the same as those given in example 3.1. So in example 3.1, we did this. I used the label A for this consumer, but now let's say this is a consumer B. The two goods are perfect substitutes to consumer B, and B has 2 units of a good 1, 3 units of a good 2. Yeah, so if these two consumers trade their initial endowments and without any production, and now we can think of a what equilibrium price and what is the equilibrium price and what is the optimal demand choice for each consumer, right? Descriptive theory of equilibrium. So now we compute the Walrasian equilibrium of this economy. So we start with a excess demand function. And now first a consumer A, because we are done with the consumer B in the previous example. So consumer A's demand function, and remember that, notice that this is a Cobb-Douglas utility, so the marginal utility is going to be positive. So if the consumer has this Cobb-Douglas, and consumer's preference relation is going to be strictly convex and strongly monotone, right? Because every good is a desirable, because derivative will be positive. In other words, marginal utility will be strictly positive. And the same for the consumer B, the linear function 2x1b plus x2b. Okay? So the marginal utility is 2 from good 1 and 1 from good 2, strictly positive. The consumer A and B, these two goods are desirable, so preference relations are strongly monotone. Alright, so we just checked these two consumers' preference relations satisfy the two assumptions in proposition 3.2, strictly convex and strongly monotone. And the initial endowment, because a consumer B has a 2,3. So there are total 60 units of a good 1 in this economy, 5 units of a good 2. So the initial endowment vector is also strictly positive. Every condition in proposition 3.2 is satisfied. And so we can anticipate the excess demand function will meet these 4 properties. All right, so now let me compute the Walrasian equilibrium of this economy. So first the x1a, optimal demand for consumer A is going to be, so in case of Cobb-Douglas, we have a nice formula. So x1 to the alpha, x2 to the 1 minus alpha. I'm not sure if I mentioned this, but a optimal demand, x1 star, is going to be alpha times his income, W, wealth, divided by P1. And x2 star is 1 minus alpha, W, over P2. So the idea is this consumer puts weight alpha on good and weight 1 minus alpha on good 2. Right? So if he has a wealth W, and alpha portion of that income or wealth will be spent on good 1. So how many units this consumer consumes? How many units of a good 1 this consumer consumes? As is going to be alpha W, the part of money spent on good 1, divided by P1. And similarly, good 2, how many units of good 2 this consumer purchase? 1 minus alpha W over P2. Okay? The X1 star alpha, A. So here, this corresponds to the case when alpha is 1/2 and 1/2. Okay? So regarding alpha 1/2, then we can find the optimal demand for good 1/2 times his income, market value of his initial endowment, for P1 plus 2P2 divided by P1. And X1 star or X2 star to star be A. Consumer A's demand, optimal choice of good 2, 1/2 times his income divided by P2. And then we can simplify each expression. So this is going to be 2 plus P2 over P1. In terms of the relative price, 2 plus P to the power negative 1, the reciprocal of the relative price, because P is defined as P1 over P2, and X2 star A, 2P plus 1. Okay? So excess demand function for consumer A, Z1, is 2 plus P to the power negative 1 minus 4, P to the power negative 1 minus 2, and Z2, 2P plus 1 minus 2, 2P minus 1. Hopefully this is right. All right. So now let me use the first property of excess demand function. So we know excess demand function is a homogeneous of degree 0. Okay? So originally demand function, excess demand function, is a function of P1 and P2, Z1, P1 and P2. But using homogeneity of degree 0, this is equal to Z1, P, comma 1. So I can divide these two prices by P2. Still, excess demand function does not change because it is homogeneous of degree 0. So I can express demand function as a function of relative price. So here, Z1 A, excess demand, consumer A's excess demand for good 1, and consumer A's excess demand for good 2. All right, so this is Z, and I rewrote excess demand for consumer B here. So that is already we found in the previous example. When P is lower than 2, this consumer consumes only good 1. But when P is higher than 2, this guy only consumes of good 2. So we have this. All right. And now let's compute the aggregate excess demand function for good 1. Z1 is Z1A plus Z1B. So now we have to split into two cases when P is higher than 2 or P lower than 2. Because a consumer B, to consumer B, the two goods are perfect substitutes. So his optimal behavior is kind of very extreme. So we divide it into two cases. So Z1 is when P is higher than 2. Z1B is negative 2, and Z1A is fixed by this. So P1 e to the power negative 1 minus 4. E is lower than 2. Now with this one plus this one, so we have 4 e to the power negative 1 minus 2. Right? And then Z2, aggregate demand for good 2, that is a Z2A plus C to B. So also we divide into two cases. When P is higher than 2, consumer B's excess demand for good 2 is 2P. 2P plus 2P minus 1. So we have 4P minus 1. If P is lower than 2, consumer B's excess demand is a negative 3. So 2P minus 1 minus 3, 2P minus 4. Okay. So once again, we know consumer A's preference and consumer B's preference are strictly convex and strongly monotone. And the first proposition in the previous lecture video says, so with these two conditions, equilibrium price is characterized by this equation. With a local non-satiation, we have inequality, but with a strong monotonicity, we have a equality. So we have a equation. Okay, so if P is an equilibrium price, then Z1 star, Z1 P and Z2 P should be equal to 0. Okay, so now we check the possibility of whether there exists an equilibrium price higher than 2. Okay, so if P is higher than 2, excess demand for good 1 is this, and excess demand for good 2 is this. Yeah, so by this proposition, we should find e to the power negative 1 minus 4 for this one, Z1, and 4P minus 1 is equal to 0. Okay? So, is it possible? Okay, so 4P minus 1 is equal to 0, then P should be 1/4, right? And 1/4 price also satisfy this equation, but we start with the assumption P is higher than 2, right? We start with this assumption, hypothesis of P is higher than 2. And then using this equation, we obtain 1/4, so have a contradiction. So we conclude there is no equilibrium price higher than 2. Now we examine the possibility whether there exists an equilibrium price lower than 2. In this case, excess demand for good 1 is this. For good 2 is this. 4P negative 1 minus 2. And 2P minus 4 is equal to 0. All right. Then 2P minus 4 is equal to 0. And P has to be 2. And if P is equal to 2, then this is also satisfied, right? But we started with the hypothesis P is strictly lower than 2. Yeah? So we conclude that there is no equilibrium price strictly lower than 2. Yeah? So we can delete these two cases. And the only remaining case is P is exactly equal to 2. Right? So that is the only equilibrium candidate. So when P is equal to 2, what is a X1A? X1A, consumer A is going to purchase 2.5 units of good 1. I can just put in 2 for P here. So 2 to the power negative 1 is 0.5. X1 star A is going to be 2.5 units. And X2A is going to be 5, 2p plus 1, right? And in this economy, there is a 60 units of a good one. Omega 1 bar is a 60 units, and omega 2 bar, 5 units. So the remaining goods will be consumed by consumer B. So X1 star B is a 3.5, and X2 star B is going to be 0. So the all initial endowments of good 2 will be consumed by A, right? Now we have to check, we have to check this bundle choice. Consumer B just consumes good 1, 3.5 units. Indeed maximize consumer B's utility. Yeah. In case of, so when P is equal to 2, every bundle on the budget line is a optimal for consumer B. So when price is equal to 2, consumer B's budget line is X1B plus X2B is equal to the market value of his initial endowment. Initially, he has 2,3. So 2 times 2 plus 3 times 1, so that is a 7. Okay, so 3.50. Now, if consumer B consumes 3.5 units of a good 1, this bundle is on the budget line. Okay, so we can say this is an optimal bundle, optimal choice for consumer B. Right? So, what is a equilibrium? The allocation X star, that is a X star A, X star B, allocation of goods to consumer A and B. So 2,5 and 5 for consumer A, and 3.5 and 0. So that is a equilibrium allocation. And what is a price vector supporting this allocation as an equilibrium? P star is 2. Okay. So these two will be a equilibrium. Right? Then we can check whether so we can check several properties here. So the excess demand function for good 1, e to the power negative 1 minus 4. So at the equilibrium price 2, Z1 P dot, so let me check the Wallace rule. Okay, so P dot Z1P plus Z2B. So, okay, Wallace law tells us P dot aggregate excess demand function vector should be 0 for every price P. When then I normalize the price of a good 2 to 1, so the dot product is going to be P times Z1 of P plus Z2 of P. I normalize P2 into 1. So Z1 of P, when P is higher than 2, is this one. So this Z1 of P is a P to the negative 1 minus 4 times P, and Z2 for P minus 1, when P is higher than 2, and you can easily check this is equal to 0, right? P times P to the negative 1, that is 1, so that will be cancelled off by this negative 1, minus 4 times P, so these two are cancelled, so it boils down to 0. When P is lower than 2, we have this 2, And you can easily check, Wallace law also holds for, P is lower than 2. P times this one plus this one is going to be 0. So once again, the one consequence of Wallace law is, although we have two equations, two conditions for equilibrium, the excess demand function for good 1 and for good 2 should be equal to 0, but we don't have to check this condition. Just say z1 of p is 0, then z2 is automatically equal to 0. Alright, so I think this is a, just one more thing. That is, so we found the equilibrium allocation, and we can check the first welfare theorem. So we can verify the first welfare theorem is indeed true, even in this economy. So allocation is allocation X star is a parity efficient, and how they verify this? Because at the parity efficient allocation, the one necessary condition in pure exchange economy is a MRS. Consumers MRS are, MRS A, MRS B agree with each other. Okay? And MRS is for consumer A is X1B, X2A over X1A. UA was X1A, X2A. Okay? So the marginal utility from good 1 over good 2. And for B, that is 2. Right? That is a fixed number. So at the equilibrium allocation, consumer A chooses 2.5 and 5, right? So, excuse me, if we put in 5 for this and 2.5 for this, yeah, we can easily see two MRSs are equal to each other. So equilibrium allocation is indeed parity efficient. All right, so let me stop here. So I think I'm done with part 1 of chapter 17. And after lunch, let me take the second video.